Welcome back to the Beyond Bones podcast, presented by the Houston Museum of Natural Science. I'm your mental curator, Johnny Hemberger. Have you ever wondered how paleontologists hypothesize about the behavior of dinosaurs and other extinct creatures? Turns out there are a number of ways, but not the least of which is by simply observing modern animals around us today. Collin Diggins is our Paleontology Lab Manager and just the person to talk to about such subjects. So sit back and relax as I join Collin and perhaps a special guest to discuss this very topic, and because we are so naturally curious, perhaps a few delightful related rabbit trails.
Looking at modern animals as an analogy to those in the past is a principle in paleontology we refer to as actualism. As far as behaviors go, we can see that in parallels with modern animals in terms of, say, hunting, right? You can see, say, wolves hunting their prey and see the ways in which they take down animals and the marks in which that leaves on the bones or on the carcass. And we can look at, say, injuries to bones of animals in the past and understand behaviors like predation. We can also learn a lot about the individual features of these animals. So to use Triceratops here as an example, we look at modern animals to better understand features that may not preserve as well. So in a great case would be, is it all right if I trot this out?
Absolutely, yeah. What
Right.
is this between us?
This here is a cast replication of a Triceratops horn core, specifically one of the brow horns. Of course, the name Triceratops, tri meaning three, refers to the two brow horns and the one nose horn. But we look at these bony horn cores, and looking at modern animals that have these bony horn cores, say something along the lines of antelope or bison, around that bony horn core we have what's called a keratinous sheath, kind of like it's made out of keratin, kind of like your fingernails, which extends the length and increases the sharpness of these horns. And there's, of course, also you notice all these pores and grooves running along here that provide blood flow that flows just underneath. You know, the very sensitive area just underneath your fingernail is another kind of good analogy. There's a lot of blood flow there, so if you cut too close, even when you're trimming, say, your dog or cat's claws, they can start to bleed very easily. There's a lot of blood flow in there. So that's one way in which we can look at features on modern animals to better understand features on animals in the past. And sort of one really great example where this has been proven without a doubt is sort of a good example of this is in, this is true of claws as well. The Field Museum just recently unveiled and prepared a new Archaeopteryx specimen that they can actually see not only the bony cores of their claws, but preserved almost as a shadow around those claws are some of the keratinous sheaths. So that is one where they've been hypothesized previously, and there's at least a very good example of it being proven beyond a doubt as a fact.
Right, and you know another example that's coming to my mind, still using Lane as an example, how we know reasonably well that Lane was a herbivore, maybe eating nuts, perhaps insects, got in there a bit as well. But you look at Lane's teeth.
Absolutely.
And you can look, what other modern large quadruped animals are herbivores, and you kind of compare their teeth. So obviously Lane doesn't have, we're sitting right next to Stan here just off camera.
Yeah.
Stan is obviously a carnivore.
Yeah, he's got those lovely serrated, serrations of course being these little bumps along the edges, just like on a serrated steak knife. We see those on modern carnivore canines as well. We see that on the canines, or on all the teeth of the T-Rex, I should say. When it comes to things like Lane, Triceratops, and herbivores, we tend to see, again, similar sorts of features showing up in their teeth, in that they, have cusps, these bumps on the surface, not unlike ours do as well, but unlike the incisors in the front of our mouth, which are very sharp, they're more akin to the ones further back, like your premolars, your premolars are probably our best analogy for teeth in our mouth that would be analogous to those in a Triceratops. Animals that have teeth like that are usually very good at shearing through leaves and vegetation of that sort. Another way of thinking about it is sort of in things like the Pleistocene or the Ice Age species. We look at something like mammoths and mastodons. Mastodons have these lovely cusps that interlock, but they're very dull compared to, say, a carnivores, making them very good at browsing on leaves. Look at mammoths, which live at the same time and in similar sorts of areas, but different environments because they have very flat teeth, very suitable for grinding. Which again, if you look at grazers today that feed very heavily on grasses, they tend to have very flat teeth, very good for grinding. Right. Which is something you don't see a lot in dinosaurs because, of course, grasses weren't very common during the Mesozoic. They don't really show up until the very latest portion of the late Cretaceous.
Right. See, that's so fascinating. All these context clues. And that's kind of the point of this episode, of this discussion, is a lot of what we theorize about dinosaurs doesn't come from nowhere. It isn't a paleontologist sitting in a dark lab saying, I'm just going to make things up.
I think this, yeah, from my imagination, indeed, yeah.
Right. You say, okay, what modern animal has this similar feature, and how does this animal act?
How does it behave? What does it feed on? How does it survive in its environment? It used to be a lot of paleontology was just interested in reconstructing these animals. More and more, the push in the science has been to reconstruct the entire environment and how they interact and how it functions. And again, not having been there to see these animals while they were living ourselves, the best way we have to understand it is to look at modern ecosystems and try and use some of those interactions and behaviors to try and model how things interacted and behaved in the past.
You know, I think it also just came to mind, a good kind of calibration, for lack of a better word, crocodiles.
Yes.
Crocodiles are still here.
Yes.
And they have been here for over 100 million years. Around what is it around?
Oh gosh, I want to say it's around 200 million, but I'm not certain on that. Our other lab technician,
verify.
Ryan, will be better at your crocodilians. But
the point is, the crocs have been here forever.
Yeah,
so when
yeah.
when you find a croc fossil that is, let's say, 100 million years old, all you need, this looks almost exactly like our modern crocodiles. Maybe modern crocs have adapted slightly to
shifts in their environments,
right,
and where precisely they're living. But generally speaking, their body plan really hasn't changed that much in the last 100 million years or more.
Right.
Yeah.
So you find a crocodile 70 million years old right next to Lane that looks like a modern crocodile. That's like a good calibration, I think.
Oh yeah, it's a great indication of the environment, at least of where Lane would have been being buried. If you say had crocodilian material associated with it, we know modern crocodiles tend to live in watery, very wet environments. It's where they are best adapted to hunting their prey and surviving in terms of reproducing and all that. So that would give us a great indication based on how we understand modern crocodilians as to what was going on in the environment in the time when Lane was living and eventually got buried as well.
Right, alongside the crocodiles.
Yeah.
So there's no real. I wonder what this crocodile ate. The 70 million year old crocodile. I wonder what it ate. It probably similar to what
modern crocodiles eat. Yes, absolutely. And when we find in the same layers of the rock the presence of bones from fish and from turtles and things like that, which again are of course things that are still alive in these environments today and naturally food as well for the crocodilians. These parallels start to make a lot of sense. They line up very nicely.
Turtles are funny to me because it seems like every time I walk into a lab, we got to get through this layer of turtles.
Yeah.
There's always turtles in not every, but in a lot of specimens that you find. It's not just the dirt matrix. Oh, here's some more turtles again. And they're the same as the other turtles we found. We have a whole collection of turtles. We definitely know turtles have been here, a similar amount of time of crocodiles and other reptiles of the sort. I think that's another kind of good calibration. Ancient turtles compared to modern turtles are very, very similar. So it's not far-fetched to consider or theorize on the behavior of a 70 million year old turtle, because it is very similar.
In terms of body plan,
right,
in terms of, all the various things that would lead us to believe that it's operating in its environment in a way very similar to modern turtles. Absolutely, yeah.
One of the things, getting back to Lane, that I find very fascinating is, one of the things as I'm the YouTube manager and podcast manager, which I get to be basically know just enough about a whole different, like a jack of all trades of kind of these scientific fields.
Absolutely, yeah.
And one of the things I find fascinating just in my, study of all these different fields, Lane's feet. One of the ways we theorize that about its environment is Lane's feet. Are there any parallels to modern large animals in Lane's feet? They don't have to look exactly alike, but what I'm getting at is kind of the pads spread out, meaning they probably walked around marshes in muddy environments, and their big flat pads help them not to sink in.
So you're getting into an aspect of Triceratops anatomy that I really don't know anything about. I'm more of a specialist in the Pleistocene, so I do know that discussions of the shapes of the feet was big in terms of referring to, say, something along the lines of our Diplodocus, and in helping to dismiss many of the early depictions of that animal existing exclusively within aquatic environments, having to support its weight in water. But in specific reference to Triceratops, I'm afraid I don't know. That's not in the area of my expertise.
That's a perfectly valid answer, and I appreciate that. Not many real scientists would. I'm just going to make something up on the spot and think with authority. That's why we love you, Collin. Is if there's something you don't want to put out that misinformation, rather than put out misinformation, we'll say, that's not an area of our expertise, or even we don't have enough context.
Data. And it's certainly, I imagine, something that somebody has studied. I have no doubt there are papers out there on it, but it's just not something I know off the top of my head.
You know what? I will link in the description of this podcast research papers about Lane's feet
or Triceratops feet in general. I don't know if anybody specifically studied Lane's feet, but Lane does have some truly spectacular feet, so that also would not surprise me.
Yeah, some of the best preserved feet
in the world, at least certainly for Triceratops,
Absolutely. I want to ask about, because it's always puzzling. My son is 4 years old. He knows more about dinosaurs than I do. It's crazy. He will line up on the bathtub a dozen dinosaurs and be like, Parasaurolophus, T-Rex, Triceratops, Iguanodon, Dimetrodon. Like, he's not even 4 yet. He's just rattling off these names. Parasaurolophus, I get messed up on that. I want to call it Paralophosaurus. Like, that's always what I want to say. But my 3-year-old currently knows that
correcting you on it.
Now it's Parasaurolophus.
Yes, sir. Mm-hmm.
So, rhinoceros.
Yes.
I've always had a fascination with rhinoceros in regards to Triceratops. I don't know if there is a huge amount of genealogical overlap between the two animals, because I got to get my animals straight here. Rhinoceros is a mammal.
Correct.
And Triceratops is a dinosaur.
Yes.
So they're not, but they both have horns.
Yes.
Very similar facial features. Can you speak a little bit to any sort of correlation between?
Yeah. So rhinoceros as a mammal and Triceratops as a dinosaur, which specifically is a subset of reptiles, last shared an ancestor sometime back during essentially the Carboniferous, which is about 400 million years ago. Or sorry, I want to say more like 300 million years ago. 400 is getting us all the way back into the Devonian. But 300 million years ago. So while they are related in the sense that all tetrapod animals, everything walking around with 4 limbs more or less, shared an ancestor that far back in the Earth's history. They do share some very interesting features. As you say, the nose horn is kind of probably the most obvious correlation in sort of their adaptations or in the way that they look. That is something that we call convergent evolution. That is sort of probably these animals are being subjected to very similar sorts of conditions or forces in their environment, and they've essentially hit upon the same solution. They've effectively reinvented the wheel, so to speak, even though they don't have that sort of feature in their ancestors.
Right.
So, another great example of this would be looking at modern dolphins and ancient ichthyosaurs. They tend to have very similar sorts of body plans, although ichthyosaurs' tails are vertical. They're swimming back and forth because they are reptiles.
Right.
Whereas mammals and dolphins tend to have their tails doing this, but they've essentially hit upon the same general body plan as a way of being fast in the ocean to hunt prey that are probably also very fast in terms of things like fish or squid or soft-bodied, fast-moving animals.
Cool.
So that's again an example of where those ancestors those animals may have shared an ancestor very far back in time, but then they've essentially come back to looking very similar just through trying to solve the same sorts of problems in their environment.
Right. Hold on. I'm going to make sure my camera is still recording here.
Of course.
We're doing it live here. I don't want to miss anything. This is so fascinating. So we can study the behavior of a rhinoceros and see and observe how does it use that horn and why. just off the top of my head, I would say for defensive purposes, probably also
Yes.
for mating, for attracting a mate. But is there, because I'm not a zoologist, I'm not a paleontologist, does it use it? Do you know if the rhinoceros uses its horn for anything other than to look good for the ladies and defense against, flinging lions left and right? Do they use it for any like foraging or anything like that?
And no, I must also admit that I as well am not a biologist or a zoologist specifically. My understanding is that it is used almost exclusively for defense and for ornamentation or for display that, look intimidating to keep the enemies at bay and also look impressive for the mates potentially as well.
Mm-hmm. Modern herbivores eat rocks. Don't some of them swallow rocks?
So it's not common amongst mammals to my understanding, but certainly we see in modern birds them swallowing stones in order to help bust up things in their food. Chickens are a great example of swallowing stones in terms of what we call gastroliths to help, say bust up insects or process plant material in their diet that they might otherwise have a difficulty in digesting. And that is actually a shared trait they share with their ancestors, the dinosaurs. That's something that we've seen in ancient fossils as well.
Speaking of, I think behind us, we got David Temple here is going to ruin the podcast. We have the dinosaurs behind us. What's their name that the T-Rex would feed on back here?
So next to the T-Rex, we have a Denversaurus, which is an ankylosaur. Oh, directly across them is the Hadrosaurus, the
that's the word I'm looking for.
Yeah.
Do we find gastroliths associated with hadrosaur fossils?
I assume so. I don't know of any instances off the top of my head again. I know that they've been associated with long-necked sauropod dinosaurs, at least. Hadrosaurs.
David, do you want to sit down with us just for a second?
In their gullet?
So hadrosaurs you have found gastroliths in hadrosaur gullets?
They also swallow their exhausted teeth.
Oh yes, the swallowed teeth. Oh
Here,
yes.
repeat that answer. I want to get you on just for a minute.
Yeah,
do you have a minute?
Come
Is
join
that okay?
us.
Okay, come sit between us. Your butt's blocking the camera right now. I know.
Cozy.
So we're gonna share the mic here real quick. It just so happens that we have two expert paleontologists. Look at this. How lucky we are to have two paleontologists in the chair right here. Can you speak towards hadrosaur, what we find in hadrosaurus gizzards that kind of analogous to modern animals swallowing stones?
In some senses, this makes me think more of a bird. So their teeth, hadrosaurs have the most complicated dental batteries that have ever been. And so when their teeth become worn, they shed them, but they'll swallow them and they'll become basically part of a crop. And so that crop will help chew and grind up tough plant particles, very similar to, say, like gastroliths and sauropods. So they'll retain those. And we have found those. First hadrosaur tooth I ever found was one of those. And I couldn't believe it was a hadrosaur tooth because it was just so tiny. But it was one that had been exhausted and worn further in the gullet of the duckbill. And then, of course, once they get where they're really, really worn down, they just poop them out. So they get carried out and they end up in the poop.
I've seen you put a coprolite in your mouth to test whether or not it's a coprolite.
I thought we weren't talking about that.
Okay,
that was a crazy bar bet.
We'll move on from there. So, David, just to let you know what we're talking about, this is for Beyond Bones podcast. We're talking about the subject specifically, and maybe we're going on some rabbit trails, obviously, about analogous modern animals to dinosaurs and the way that we come up with these theories about ancient dinosaurs by observing similar modern animals. And we got onto this subject specifically right now as you sat here of gastroliths and finding stones in dinosaurs or associated with dinosaur skeletons that are analogous to, as Collin said, the way chickens eat. Chickens will swallow stones and it helps them in the digestive system. Are there any modern animals that you know of that will swallow on purpose their exhausted teeth?
Not so much the exhausted teeth, but I don't know if Collin, did you discuss crocodilians?
I did not. That was the one I was going to mention. Yeah,
crocodilians will definitely swallow stones and rocks similar to gastroliths. And it's unclear. They do seem to use them to help grind up their food because, as you know, crocodilians, when they eat things, they eat the whole thing. So they eat the skin, the hide, the flesh, of course, the bone, and it helps them crush things up. Paul Sereno did an interesting study with Super Croc. It was on that Brady Barr documentary years ago, about where they had crocodilians swallow sensors. So they were measuring stuff in their stomach, and then later they would retrieve the sensors, and the sensors had been crushed and torn up, even though they're very hard plastic, by gastroliths and things that they had swallowed. But there's also thought that it does do that. But they also think they may help them to create negative buoyancy, so they can dive down and stay down. So they're using it for weight, but they're also using it for digesting food.
Can we speak about something that is quite controversial at the moment, Lane's skin for a moment? This is all within the context of observing modern animals and coming up with theories about dinosaurs by observing modern animals. Collin, you mentioned in a previous video, and we are very clear that it's a controversial theory. The theory is that Lane may have had quills or feathers. And you look at these keratinous scutes and these impressions that we have Lane's skin impressions back here we can observe. Collin, you mentioned that, so in osteoderms.
Yes.
Now, the osteoderms means that these scutes or whatever have a bony structure within them, but we have not observed that in Lane, which lends a little bit of credence to maybe these dimples on his skin could be quills. Can you speak to the Lane's quill theory or feather theory in terms of what we observe in modern animals?
So I'm sorry, I'm just trying to kind of parse what your question is. Osteoderms are a very specific bony structure. It's the name literally means osteobone, derm, skin. It's bones spread throughout the skin. So we see them in modern animals, in crocodilians, alligators, those sorts of things. Armadillos are an example of osteoderms in mammals. They are found in dinosaurs as well. Obvious examples would be things like the Ankylosaurus, those armored plates on the backs. Those are osteoderms. And usually associated with those osteoderms on the outside of the skin is something called a scute, which is made out of keratin, just like our fingernails, just like the proposed horn on the outside of the core of like Triceratops. So where you find those osteoderms, those bony plates, the scute on the outside is, you might say, implied. There's a suggestion that it could be there. So with Lane's skin, because we don't have associated with Triceratops any osteoderms, the idea that there is a keratinous scute on the outside, to me, doesn't seem very likely. Now, that isn't to say that these aren't scales that then might also be keratinous as well, but it's not necessarily what I would call a scute. Right. Just because that tends to be a very specific sort of anatomical feature, again, associated with a bony osteoderm.
And so the main thought is that there's not necessarily a bone structure that underlies.
Yeah.
And that does support the quill
theory as well. Yeah, absolutely. Because all feathers and quills, in birds at least, are essentially just adapted scales. So again, they're made out of keratin, just like a fingernail as well, but it's just a sort of a different structure than, say, what I would call a scute.
Right. And part of this theory, if I remember you mentioning, and we're getting slightly off topic here a little bit, is Triceratops ancestry. There was an ancestor of Triceratops that was found with quills. That's a question we get a lot. Whenever we bring up this theory of quills or feathers on Triceratops, the biggest question, and it's completely valid, is where's the quills then? How come we haven't found any feathers or quills associated with Triceratops? All we found are quills associated with an ancestor millions of years prior. But again, that's kind of where the theory comes from, is because an ancestor had these. It's not completely far-fetched. Turn off your phone, David.
I'm sorry.
It's okay.
You've just answered your phone.
It. Yeah.
We'll call you back.
All right.
Anyways, so that's part of the theory, is that you look at the scutes, you look at the ancestry of Triceratops, and that supports a hypothesis that perhaps Triceratops may have had quills. It's perfectly valid. No, we have not found any quills associated with Triceratops skin yet.
Yes.
But who knows what we'll find later. We're not saying assertively
That it will be found.
That it will be
yeah.
found or whatever. But we found ancestors of Triceratops that did have it. And then we find these scutes on Triceratops that we can't find the bony structure. We can't find the osteoderms with it. So when there's if there's an osteoderm, can there ever be a quill or a feather with an osteoderm?
I don't know of any quills or feathers associated with osteoderms. I do know that, again, in using a modern animal as an analogy, when we're looking at armadillos, they tend to have hairs that sprout along the edges of those scutes. So it's not out of the question in my mind. I don't think it would be impossible.
And I don't think it would be impossible. And we'll start wrapping up the podcast here because we're drifting a little bit.
Yeah.
Well, one quick point to that
Sure.
is the Triceratops ancestors where quills are preserved. That's from a very, very, very high fidelity preservational environment. So it's known as a Lagerstätten. So it does preserve soft tissues. Yeah. Where typically most of the later examples of Triceratops are not found in that kind of environment.
Yeah, the preservation on those specimens in particular is really pretty exquisite, and we don't tend to see that level of preservation in our later Triceratops.
No, not at all. And also Triceratops skin is vanishingly rare. So Houston has, I don't know if it's the only known example, but it's probably the best known example. So, which is why a lot of scientists are interested in our stuff. So, it's very possible that it may have been that way, it just didn't preserve.
And if you look at, and again, we'll start wrapping it up here. If you look at, because it ties it all together, observing modern animals to help hypothesize about ancient animals. If you think about an elephant, do you think that people might think, oh, it's kind of a hairless, maybe the first thing that comes to mind isn't fur or hairs or follicles. It's obviously the ears, the
trunk,
the ivory, all the big characteristics of an elephant. But elephants do have very thick follicles, very thick that are similar. They're not exactly like quills, but they're in the same family of chemical makeup and whatever, like fingernails and hair and thing like that.
Yeah.
And they're very thick. Mm-hmm. You might be confused. Somebody might find that super thick hair and be like, this is just as big as a porcupine quill or similar size to a porcupine quill. So are we splitting hairs, so to speak, calling something a quill and a feather in a hair?
Well, it is, they all sort of share, it's one of the things that the idea of evolution is it doesn't create something from nothing. It has to exist by modifying existing structures. Mm-hmm. So all of our hairs, quills, things like that are modifications of earlier scaled ancestors. These are earlier structures existing that were shared across these creatures and of course are made out of the same material, and that they are often being used for the same sorts of purposes, for insulation, for display, so that they are very much analogous. They look slightly different because they've arrived at these same sort of destinations from slightly different ways, but all starting from the same point as well.
It's all truly fascinating. Thank you all both now, David, for just popping in here on the Beyond Bones podcast. I can't reiterate enough. We talk about all these things, and I'll put links in the description here to various concepts that we discussed, maybe different research papers that dive deeper into this discussion. I can't reiterate enough. Come to the Houston Museum of Natural Science. Come through our front doors. Come see Lane, and then turn your head right over here, maybe 15 feet away, and observe Lane's skin. And you can start hypothesizing your own theories and kind of see how things are connected. Observe in our animals the similarities between the animals we have here on display, and then you can walk across the street literally to the zoo and then observe those large animals and start saying, well, they had similar looking features. The point is, come to the Houston Museum of Natural Science. Observe these things for yourself. Is there anything else you'd like to add, or can I put a bow on this?
I'd say, put a bow.
Oh, there'll be more. Well, we will discuss way more about this in future episodes of Beyond Bones podcast. Thank y'all so much for listening. Be safe and stay curious.